Today we're going to look at lecture number 4, which is the last lecture that we're going to do in chapter number 3. And for learning goals, we have only one learning goal for today, which is to identify the velocity of a moving body as seen from different frames of reference. So that's the goal that we want to achieve for today. Now we'll start with relative velocity. And what you see here, you see 4 planes in an air show moving with a speed v. That means all of them moving with the same speed here. And there are 2 questions that are asked here. The first one, what is the velocity of one of the planes with respect to the ground? And the second one, what is the velocity of one of the planes with respect to one another? This brings in the question of relative velocity here. Relative to what? In the first question, they ask you relative to the ground. Okay. And in the second, with respect to one another. So if someone is on the ground and looking at the planes, he will see the planes that are moving with the speed v. But if one of the pilots look at the other plane, since both of them, they're moving at the same speed, he will basically say the other plane is not moving relative to me. Okay. And that's the idea here when we talk about relative velocity. So the velocity of moving body seen by a particular observer, we say velocity relative to that observer. So it depends from which frame. A frame of reference is a coordinate system plus a time scale. That means if someone is moving and things like that, that's how we measure things. So let's look at relative velocity in one dimension. And we'll start, as you remembered, in chapter number 1, we talked about position x, and then we talked about velocity vx, and we said this is equal to dx by dt. So we're going to look at 2 frames here. We're going to look at a cyclist, and we're going to give it the symbol A, and the cycle is stationary. And then you have a moving train, and we're going to give the train symbol B, and then a passenger inside the train, and the passenger is moving relative to the train. So when we talk about the passenger here, and we want to look at the position of the passenger, we have to say relative to what? So if we take this relative to the reference frame B, which is the train, that means relative to the train, we will say that the position x, and we put a subscript P/B, and P here stands for passenger, and B here stands for train. That means the position of the passenger relative to the train. Now, we're going to look at the position of the train relative to reference frame A, which is the cyclist outside, the stationary one. And in that sense, we're going to say x B/A. That means the position of the train relative to A. and A here is the stationary frame of reference for us. Now, if we go back to the passenger, and we can ask the question, what is the position of this passenger relative to frame A, which is the stationary frame now? Now, the cyclist A here will see the train moving and see the passenger moving inside the train. So the position of the passenger relative to A, which we say X subscript P/A, that means passenger relative to the frame reference A, should equal to the position of the train relative to the observer A plus the position of the passenger relative to the train. And that's how we're going to define the position of the passenger relative to this observer here, or cyclist. So it always depends relative to what? Are we measuring the passenger relative to the train, or are we measuring the passenger relative to the observer? So from the point of view of the cyclist here, that's how he's going to determine the position of the passenger. The position of the passenger P relative to A equals the position of the train relative to A, how the train is moving relative to the observer A, plus the position of the passenger relative to the train. Now, if we want to get the velocity, then the velocity of the passenger, and we use here x because it's only moving along the x-axis, it's one-dimensional, it will be dx by dt, and of course in this case it will be dx passenger relative to the observer by dt, and of course dx relative to a dt will give you v p relative to a dash x, and dash x here meaning along the x-axis because it's one-dimensional motion, it's a velocity here. Okay. And I'm not putting an arrow on the top because I'm only talking about a component, one component, which is the x component, plus the velocity of the train relative to the observer along the x-axis, plus the velocity of the passenger relative to the train along the x-axis. I'm just taking this one, VBA, it's dxb relative to a by dt, and VP here relative to b, it will be the dxp relative to b by delta t. So this here will give me the relative velocity, and this one will give me the relative position in one dimension. Now you can basically set your x-axis, that's basically the x-axis. One frame here, you have the origin which we call OA, and that's the origin of your observer, the frame of the cyclist. Now you have another frame, which is the frame of the train which is moving, and that's why we call it here AOB, which is the origin of that frame, which is B. Of course, this frame is moving with a velocity B relative to A. And that's how we are basically looking at position relative to different frames, either the train or the cyclist. And we can also look at the velocity relative to the cycles, or you can do it relative to the train. Is this point clear? Any question on this one? So that's how you basically look at your relative velocity in one dimension. Now we extend this, okay, as we did in chapter 2, and we did that in 3 here. In chapter number 1, we talked about, when we talked about position, we talked about x. But when we talked about position in 2 or 3 dimensions, we talked about an r, and we said that it's xi plus yj plus z k hat. So in this case, we're only talking about the one component. And here, now you have what? You have a position vector in 2 or 3 dimensions. So you can basically now look at a cyclist, which is a frame of reference A. You look at train, and again, we say the train is B, but the passenger inside the train is not moving in the x direction. It's moving now across the train this way. So in this case, you are not talking about only an x component. In this case, the train is along the x, but the passenger is along the y. So if we want to look at the position of the passenger relative to the observer or the cyclist in the previous slide, then we have to do that in 2 dimensions, and we can do that in 3 dimensions as well. So instead of just looking at position, we're going to look at a position vector. So the position vector here, which is r vector of the passenger relative to the observer, which is a here, should equal the position vector of the train relative to the observer plus the position vector of the passenger relative to the train. We're not doing anything new. We're just basically expressing the position as a position vector. And in 1 dimension, we talked about Vx. Here, when we talk about V, it will be the Vx I hat plus Vy j hat plus Vz k hat. So it is now a velocity vector. So your velocity vector now, it will be the dr of the passenger relative to A by dt. And that will give you your relative velocity. That means the passenger relative to A. So if we do that, I will get V P relative to A. And of course, you see a vector sign on top of V here. In the previous slide, you see that we have what here? We have an X. It's only an X component. But here, you don't see an X here. Okay, you have an arrow on the top. That basically contains X component, Y component, and Z component, and so on. So the relative velocity of the passenger relative to the observer, which is A, should equal to the velocity of the train relative to A plus the velocity of the passenger relative to the train. So now we have extended the relative position to a relative position vector and the relative velocity in 1D to a relative velocity vector. So if we go back and we want to look at our frame, so for the cyclist, well, you have 3 axes here. You have the X, you have the Y, you have the Z, and that's the origin of your of the frame. Now, this is basically the position vector of the train relative to A. So that's now the train is here. But the train also will have an XB, which is the x-axis of the train, YB, which is the y-axis of the train, and ZB, which is the z-axis of the train. And that's, of course, the origin of the axis inside the train. Now, this one here is your position vector of the passenger relative to the train. And you can see here the tail is coming to the head of this. Now, this is the resultant vector, which is coming as the addition of RB/A plus RP/P. And that will give you your resultant vector, which is RB/A. That means the relative position vector of the passenger to the train. So that's basically how you will look at it in terms of these two different frame of references. Is this clear? Any questions so far? Now, if you look at this figure that we have here, they tell you that the train is moving in the x direction with a speed of 3 meters per second. And they tell you the passenger here is moving along the y-axis of the train with 1 meters per second. So if you look at the observer that is outside, okay. Now, this is the velocity vector of the train relative to the observer, which is 3 meters per second. And this is the velocity of the passenger relative to the train, which is 1 meters per second along the positive y-axis. Of course, this will be the resultant vector or the relative velocity of the passenger relative to A. So the idea here, when we're talking about the velocity of the passenger, we'll say relative to what? Is it relative to the train? That's what you have. Is it relative to the observer outside? And that's what you have here. So now you can measure velocity from different reference frames, and you really have to talk about what this relative velocities. Is this clear? Any question on this? Now, let's take an example here, and we'll take probably an example in one dimension to illustrate the point and illustrate the logic as well. You drive north at a constant speed of 88 kilometers per hour. A truck in the other lane moving south at constant speed of 104 kilometers per hour. And they ask here, find the truck's velocity relative to you and your velocity relative to the truck. So it's one-dimensional motion here, okay? And you can choose, well, you can say that this is your y-axis, and you can say that this is the x, but you're only moving along the y. Now, these are basically your directions here: north, south, east, and west. We're going to use the symbol C for the car and symbol T for the truck. And we're going to use the symbol E for earth, because both the car and the truck are moving on the earth. Now, you are probably sitting on a chair and you don't feel anything moving, but the earth is revolving around the sun, and it is rotating around its axis of rotation. But you don't feel that because you are in this frame. So we are basically measuring the movement of the car and the truck relative to the earth. So we're going to say here that the speed of the car relative to the earth is 88 kilometers per hour, and of course it's moving where? It's moving north, and we can say that it's positive for us. And we can talk about the speed of the truck relative to the earth, and in this case it's 104 kilometers per hour, and it's going where? It's going south, which is negative. So now I can basically talk about velocities. So I'll put a dash y here and I put dash y here, meaning it is the y component, because I included the minus here. So it is now a velocity. So I'm talking about the velocity of the car relative to the earth. It's 88 kilometers per hour north, and the velocity of the truck relative to the earth is minus 104 kilometers per hour, which is south in this case. Now they ask me here the velocity, the truck's velocity relative to you. That means relative to the car. So they send velocity, I will put dash here y, meaning the y component in this. You can use the x, but we can say, since it's moving along the north-south, we can use y here. So it's relative, okay. Relative to what? Okay. Now they told you relative to you, which is the car. If we just look at what we did previously, when we looked at the velocity of the passenger relative to the observer. So in this case here, we're going to look at our stationary frame as the earth. So we're going to say that the velocity of the truck relative to the earth, and let me put y here, meaning it's only the velocity relative to, which is the y component of the velocity, is one-dimensional. It will be the velocity of the truck relative to the car plus the velocity of the car relative to the earth. I'm putting the y here to indicate it is only the y component of the velocity here. Exactly in the same way. So we're using the earth here as the frame of reference where things are measured from, the stationary one. But now you're going to look at the frame of the car where you're going to measure things from. And that's why we say here the velocity of the truck relative to the earth will be the velocity of the truck relative to the car plus the velocity of the car relative to the earth. Now the velocity of the truck relative to the earth, it is minus 104 kilometers per hour. And the velocity of the truck relative to the car, this is what we want to find. And the velocity of the car relative to the Earth, it is 88 because it's moving north. So you want to find this one here. So you can take this to the other side there. And if you take that to the other side, you will take it with a minus sign. So what you have here, the velocity of the truck relative to the car, it's equal to minus 192 kilometers per hour. Now, to think about this logically, now if you are in a car and you are on a highway and the highway has trees beside it, and if you look to the side, you will see the trees moving. Actually, the trees are not moving. You're the one who is moving. But from your frame, you think these trees are moving. So now let's look at the truck here. If the truck is stationary, not moving, and the car is moving toward the truck, now in that case, you will look at things relative to you. So you feel the truck, even the truck is not moving, you will feel the truck is coming toward you, even though you're the one who's going toward the truck. So the truck will be moving, if you're moving north, the truck will be moving south relative to you. And if the truck is not moving, stationary, and you're moving at 88 kilometers per hour north, now you will think that the truck is moving south toward you, which will be minus 88 kilometers per hour. But in our case here, the truck is not stationary, it's moving. And it's moving south at 104 kilometers per hour. So you have to add this in. So from your point of view, the truck is moving toward you, toward the Earth at 104, and of course you're moving toward the truck. So you're adding both of these, and the truck may actually feel as if it's moving at minus 192 kilometers per hour. That's the logic for it here. And that's how we basically go about solving this. Now, if we now look at the second and says your velocity relative to the truck. So now you're concentrating on the car. And what we're going to say now, we're going to say that the velocity of the car relative to the Earth, and I'm going to put here /y, meaning along the y direction, which is only the velocity, y component of the velocity along this direction. It's going to equal to the velocity of the car relative to the truck plus the velocity of the truck relative to the Earth. The Earth here is stationary to you, but the car and the truck basically moving relative to this, but you're measuring from a different frame, and now it is the frame of the truck. Now, the velocity of the car relative to the Earth is 88, going north, positive. The velocity of the car relative to the train, to the truck, that's what you want to find out. And the velocity of the truck relative to the Earth is minus 104. You can take this to the other side here. And if you take this to the other side, it will become positive. That's why you have 88 plus 104, and it will give you 192 kilometers per hour. So relative to the car, the truck is moving south at 192 kilometers per hour. Relative to the truck, the car is moving at 192 kilometers per hour, but it's moving where? It's moving north. So the velocity along the y of the truck relative to the car, it will be basically minus the velocity of the car relative to the truck. The speed is the same. Now, if I ask you what is the relative speed, it will be 192 kilometers per hour in both cases. That's speed, because the speed is always absolute value of velocity. But if I'm talking about velocity or relative velocity here, well, from your point of view, which is the car, you will feel that the truck is moving south at 192 kilometers per hour. The truck will see the car moving north at 192 kilometers per hour. Is this clear? Any question on this one? So you can say that we substituted E for A from the previous example that we dealt with. Is this clear? Now, let's apply this probably here a little bit more challenging. Okay. A girl moving at 800 kilometers per hour on roll plates, and a boy is moving behind her at 5 meters per second. The girl tosses a ball backward toward the boy, giving it a speed of 12 meters per second relative to her. What is the speed of the ball relative to the boy? So in this case, it's one-dimensional motion this way along the x-axis. So the girl is moving at 8 meters per second along the positive x-axis. The boy is behind her, moving at 5 meters per second along the positive x-axis. But the girl now tosses a ball backward at 12 meters per second, but relative to the girl. Now there is an observer here, and the observer here is stationary, and he's basically on the earth. So to apply what we learned, we're going to use a symbol G, capital G for the girl, capital B for the boy, and small b for the ball. Now, we're going to look at the speed of the girl relative to the earth, which is 8 meters per second. So we can basically put a subscript here, x. Now we take it as a velocity relative to the along the x-axis. Okay. Let me just put an x here. That means it's along the x-axis, which is 8 meters per second. The velocity of the boy relative to the earth as well, because that's the station. It's also 5 meters per second. Both of them are positive because they're moving along the positive x-axis. The velocity of the ball relative to the girl is minus 12 meters per second because it's moving in the opposite direction. Now, what they want from us here is they want the speed of the ball relative to the boy. I did not put an x here because we're just looking at the speed here. And you know that the v of the ball relative to the boy, it will be the absolute value of the speed of the velocity of the boy relative to the ball of velocity. Okay, the absolute value of that. Now, if I concentrate on the velocity of the ball relative to the earth now. Now, the velocity of the ball relative to the earth along the x-axis will be equaling the velocity of the ball relative to the boy along the x-axis plus the velocity of the ball relative to the earth along the x-axis. Is this clear? We can do the same thing, by the way, here. I will say the velocity of the ball relative to the girl along the x-axis also going to equal to the velocity of the ball relative to the girl along the x-axis plus the velocity of the girl relative to the earth along the x-axis. This is for the velocity of the ball relative to the earth along the x-axis, and this is the velocity of the ball relative to the earth along the x-axis, but now to the girl. So I can equate both of these since I have the same thing. So the velocity of the boy relative to the girl along the x-axis plus the velocity of the girl relative to the velocity of the girl relative to the earth along the x-axis should equal the velocity of the boy, the ball relative to the boy along the x-axis plus the velocity of the boy relative to the earth along the x-axis. Now the velocity of the ball relative to the girl, it's minus 12. The velocity of the girl relative to the earth is 8. The velocity of the ball relative to the boy, this is what I want to find. And the velocity of the boy relative to the earth is 5. So I can take this to the other side, the 5. So the velocity of the ball relative to the boy along the x-axis will be minus 12 plus 8 minus 5, and that gives you minus 9 meters per second. And that's the velocity of the ball relative to the boy. What they ask us, they ask about the speed. And of course, you always take the absolute value of that, and you will get 9 meters per second. Now, they ask you here the velocity of the ball relative to the boy. So you have to be careful. How about if they just ask you what is the velocity of the ball relative to the earth? And this is what we want to find here. Now, the velocity of the girl relative, the ball relative to the girl, it's minus 12. And the velocity of the girl relative to the earth is 8. So you will get here minus 4 meters per second. Just if you're wondering. Okay. So the ball, in this case, we can say it has a velocity of minus 12 meters per second relative to the girl, and it has a velocity of minus 9, the ball has a velocity of minus 12 meters per second relative to the girl. It has a velocity of minus 9 meters per second relative to the boy. And it has a velocity of minus 4 meters per second relative to the earth. So you always have to be careful what you're asked to find out. But since you're measuring things relative, so in this case, you can look at the observer here, and this is basically the earth because it's stationary. And you're measuring things relative to the boy. Or you can measure it relative to the girl. And that's how we solve this problem. Is this clear here? Any question on this one? Any question? So that's basically how we deal with a problem with the sort. Now, here we're going to look at something that we have in 2 dimensions. Okay. An airplane canvas indicates that it is heading north, and its air speed indicator shows that it is moving through the air at 240 kilometers per hour. If there is a 100 kilometer per hour wind from west to east, what is the velocity of the plane relative to the Earth? So the plane indicates that it's moving where? It's moving north. The speed is measured inside the plane as 240 kilometers per hour. That's the indicator there. Relative to what? Relative to the air. Okay. But the air itself, there is a wind, and if you look at your direction, this is east, west, north, and south. And the wind is going this way. It's going from west to east. That's the wind. So if you look at the airplane is heading north this way at 240 kilometers per hour. But the wind is basically going toward the east at 100 kilometers per hour. So the wind is going to push on the plane. And the plane is not going to go that way. It will basically go this way here. If you ask the pilot inside the plane, he will say, I'm going north. I'm moving north. I am putting my compass to go north. And I'm going at that speed of 240 kilometers per hour. Relative to what? He say, I am in the air, so I'm relative to the air. But the air here, there is a wind, and that wind is going east at a speed of 100 kilometers per hour. And that causes the plane to be affected by this wind. To someone on the ground, you say, no, the plane is not moving north. The plane is moving this way. And this is where you have to consider in these relative effects. So to solve this problem here, we're going to use the symbol P for the airplane, symbol A for the air, and we're going to say that the speed of the plane relative to A, it's equal to 240 kilometers per hour. I did not put an arrow on top. I'm just taking the magnitude here, indicating that speed. And it's moving north, so I'm putting in a J hat here, which is along the Y. If I choose, this is my X and this is my Y. And the speed of the air relative to the Earth, the wind is blown relative to the Earth, and we use A here for the air, and the air is moving east at 100 kilometers per hour, and I use the symbol I hat for it here. So again, the velocity of the plane relative to the Earth, it will come from the velocity of the plane relative to the air plus the velocity of the air relative to the Earth. So you're combining these two to give you your velocity relative to the Earth. Again, I'm not putting an X or Y because that's two-dimensional motion. Now, your velocity of the plane relative to the Earth now. When you look at the velocity of the plane relative to the air, it is 240 north. That's what the pilot is thinking. He's moving north. Now, the velocity of the wind or the air relative to the Earth is 100 along the positive x-axis, which is I hat. Now, you can calculate your speed, and we say here the speed VB relative to E, and of course there is no arrow on the top, meaning that I'm taking the speed. It will be the positive square root. Remember, whenever you take speed, it's a magnitude, so you're only taking the positive root of 240 squared plus 100 squared, and this will give you 260 kilometers per hour, and that gives you your speed. Now, what is your direction? Now, if we want to take the direction relative to the north, because the pilot, he is saying I'm moving north. So if I take the alpha here, which is relative to the north, the 100 will be opposite, and the 240 here will be adjacent. So tan alpha will be 100 over 240, which will be 10 over 24. So alpha will be tan inverse of 10 over 24, and it gives you 22.6 degrees. So we say that the plane is moving at relative to the ground, it's moving at a speed of 260 kilometers per hour at an angle of 22.6 east of north. Now you have the direction, and you have what? You have the magnitude. Now you may want to say, well, I want to use the x and the y. So in that case, your y component will be the, so it will be, if you're using this angle here, theta, the y will be the 240, and the x will be 100, and you can measure your angle relative to the positive x-axis. But when you're moving relative to direction, you have to do it this way. So if the pilot is starting from this point and is going north, he's not going to end up being here. He is going to be in this location here, due to the wind. So if he wants to end up this way, well, the starting point, he must start something like this. Okay. So he may point the plane at 22.6 west of north, okay, and probably he will end up there. So that's why here we also have to include in the relative motion. If a plane is moving in the air, we have to include in the air speed relative to the earth, or if it's going in a river or a sea, we also have to look at the flow of the water or the currents, in which direction and so on, and that will also affect in which way the boat or the ship will be moving. Is this clear? Any question on this? So that's basically when we look at relative motion. Let's take this example here, maybe to illustrate the effect of which direction you should take. Okay. A 0.14 kilometer wide river flows with a uniform speed of 4 meters per second toward the east. It takes 20 seconds for a boat to cross the river to a point directly north of its departure point on the south bank. What is the speed of the boat relative to the water? Now, they tell you the river is 0.14 kilometer wide. That means it's about 140 meters, okay, wide. Now, the boat, if this is the river, the boat is starting from here and ends here. It gets to this point here. but the water flows this way. So if the boat goes this way, it's not going to end up being here. It will end up somewhere here. For the boat to end up at this point, he has to start something like this in order to get here. And this question here, they tell you that this from here to here is 140 meters, and it takes 20 seconds to get there. So what was the speed of the boat relative to the water? So we're going to use a symbol R for the river, symbol B for the boat, and the speed of the boat relative to the earth, because the boat will start from here and ends here. And that's what we're going to consider as the speed of the boat relative to the earth. And that basically will be 140 meters in 20 seconds, and that will give you 7 meters per second. That's the speed. However, if, as I told you, if the boat goes this way, it's not going to end up being here. So it has to start somehow in this direction to end up being there. So this is the speed or the velocity of the boat relative to the earth. I want to start from here and come here. But then I have the speed of the river relative to the earth, which is moving that way at 4 meters per second. In order to account for this, I'm not going to go straight that way. I'm going to go this way. And this is basically the speed of the boat relative to the river. I will go this way. Now the flow will push me that way. I will end up there. So from this triangle here, you will say that the speed of the boat relative to the river, it will come from the velocity of the boat relative to the earth. The velocity of the boat relative to the river will equal to the velocity of the boat relative to the earth, plus the velocity of the river to the earth. We put it here, earth to the river, just to show you that we can cancel the E with the E and we get the boat relative to the earth. Now, the velocity of the boat relative to the earth we want to achieve, it's 7, and I will use J hat because it's moving along the positive y-axis. Now, the velocity of the river, it's minus the velocity of the river relative to the earth. And in this case, it's equal to minus 4 I hat. I'm putting here a plus, but now when I want to include it in there, I want to get the velocity of the boat relative to the earth. So now my velocity here, which is, or the speed of the boat relative to the earth, and when I take the velocity of the boat relative, the speed, it will be the absolute value of my velocity, which is the square root of 7 squared plus minus 4 squared, and you get this. Now, you have to look this as a triangle here, and that's by Pythagoras law. If you think of that, it will be the VBI r squared, because that will be the hypotenuse. It should equal to the VBE squared plus the VR relative to the E squared. Okay. And that's basically how you will end up with this speed, and you can also figure out the angle here, and you can decide at which angle you're going to point in order to end up at this point here. Is this clear? Any question on this one? Any question on this one? Okay, good. We have here another question to deal with. The pilot of a light airplane with an airspeed of 200 kilometers per hour, and we use here V slash W, and W here means wind. Okay. Wants to fly due west. There is a strong wind of 120 kilometers per hour blowing from the north, which is basically the wind relative to the earth. If the pilot points the nose of the airplane north of west so that her ground track is due west, what will be her ground speed? So there is wind, right? And this wind is basically blowing from the north. So the wind is coming from here. And that's why we said V wind relative to the earth is coming from the north. So it's blowing this way. And the pilot relative to the earth wants to go west this way. But if she does that, the wind will basically put her somewhere here, and we don't want that. So instead of doing that, she points the plane this way, and this is basically the plane relative to the wind. And then the wind will push her down in order to end up getting where? West. So they want us here to find the speed relative to the ground. So we're going to use a symbol P for the plane, W here for the wind, and E here for the earth. Now the wind relative to the earth is 120 kilometers south because it's coming from the north, so it's going toward the south. We want the velocity or the speed of the plane relative to the earth to be west. And they tell me that the speed of the pilot relative to the wind is 200 kilometers per hour. But what they want is basically they want the speed of the pilot relative, or the plane relative to the earth. If you sketch this now, this is what you want. You want to go west. So that's V of P relative to E. The wind is going down this way. And this is basically the plane relative to the air. So she has to point, as they told you here, she has to point the nose west, north of west. So she goes north of that. Now, if you look at this right angle triangle here, so the V B relative squared will equal to the VB relative to the Earth squared plus the V wind relative to the Earth squared. And you want this one here. So you have to take this the other side with a minus sign. Okay. And that's why we say that the VB relative to the Earth is equal to the square root of VB relative to the N squared minus V wind relative to the Earth squared. And it will be 200 squared minus 120 squared, and you get 160 kilometers per hour, and that's the right answer here. You have to think about this when you sketch, okay? And you're after this, you have to look at it in terms of Pythagoras theorem, and you will find out that's why we said that it is the VB relative to the wind squared minus the V wind relative to the Earth squared. Is this clear? Is this clear? And that's why C here is the right answer here. If she points west, she will end up being somewhere here, and that's not what we want. So she points north of west, and the wind is coming from the north, so she will end up basically going where? Going west. And we take this effect in. Is this clear? Any question on this? So when we try to analyze the motion of object, remember in chapter number 1, we started from a position, and then we looked at velocity, and then we looked at acceleration, and then we derived kinematic equations under one condition, which is constant acceleration. And then we took special case, which we called free fall. That means you're no longer in control, but we took it along one dimension, which is perpendicular to the surface of the Earth, which basically goes toward the center of the Earth, and we substituted the acceleration there with minus g. That's what we did in chapter number 2. In 3 here, we basically extended the motion to 2 or 3 dimensions. So instead of talking about a position, we talked about position vector. Instead of velocity, we talked about velocity vector. And instead of acceleration, we looked at acceleration vector. And of course, each will have an x, y, and z components, I hat, j hat, and k hat. And we looked at a special case, which is a free fall in 2 dimension. And we said when you have a projectile motion, you will have something vertical and something horizontal. And we took the vertical along the direction of a gravity. So we took the ay there as minus g, and we looked at x. We said we have 0 acceleration along the x. And then we came to circular motion. Circular motion as well. It is a motion in a plane. And we said when you go in a circular motion, you need to change your direction of your velocity, and we talked about parallel, which is tangential, and we talked about perpendicular, which we call centripetal or radial acceleration, and we did that in the last lecture. Today here, we looked at relative motion. From what frame of reference you are basically looking at things. But that also has a consequence when you are looking at an airplane in the air, or a boat in a river, or moving through waters. In the case of the air, you really have to consider the effects of the wind. In the case of water, you have to look at the flow of water, and looking at this relative velocity, you can basically correct the heading of your direction to get to your final destination. Is this clear? Is this clear? Any question on this? Good.